Every day, we trust our lives to bridges. We drive across steel and concrete structures that stretch for miles, carry trucks heavier than a house, and survive storms, earthquakes, and decades of wear. Most of us never think twice. We just assume they'll hold. And almost always, they do. That's remarkable when you consider what bridges endure. Constant vibration, temperature swings that make steel expand and contract, wind strong enough to move buildings, and the weight of thousands of vehicles at once. Yet catastrophic failures are rare. So how do engineers design something so long, so exposed, and so heavily loaded, yet strong enough to feel effortless beneath us? What hidden systems keep these giants standing when so much could go wrong? Bridges seem simple, a flat road in the air, but each one is a carefully balanced machine. They stretch over rivers and valleys, connecting cities and economies. Yet when one fails, the results are devastating. The collapse of the I-35W bridge in Minneapolis in 2007 killed 13 people and injured more than 100. The 1940 Tacoma Narrows disaster sent an entire roadway twisting and tearing apart in the wind. Failures like these are rare, but the stakes are enormous. Every modern bridge must hold not just its own weight, but the pounding of traffic, the shifting of foundations, and the push of storms and earthquakes, all for decades, sometimes more than a century. Engineers design them with huge safety margins, but those choices are invisible to most of us. To understand what makes bridges so strong, we need to look at how their designs evolved, what forces they fight, and the hidden features that keep them standing year after year. Humans have been building bridges for thousands of years, but early designs relied on simple materials and geometry. The ancient Romans perfected the stone arch, a shape that channels weight into compression so the bridge doesn't collapse under its own load. Many Roman stone bridges, like the Pont de Gare in France, still stand after nearly 2,000 years. The Industrial Revolution changed everything. The arrival of iron and later steel allowed for longer spans and lighter structures. Truss bridges, a web of interconnected triangles, appeared across the 19th century, letting engineers cross wide rivers and deep valleys without massive stone supports. Then came suspension and cable-stayed bridges. Instead of relying on heavy piers, these designs use cables to hang or hold up the roadway, creating record-breaking spans like the Golden Gate Bridge in 1937. Each breakthrough also came with hard lessons. The Tay Bridge disaster of 1879 exposed the dangers of wind. The Tacoma Narrows collapse in 1940 showed how aerodynamic forces could tear apart a poorly designed suspension span. Modern bridges combine centuries of knowledge with advanced materials and computer modeling. The failures of the past forced engineers to overbuild, calculate wind and seismic loads, and include safety margins that keep today's structures standing under stresses ancient builders couldn't have imagined. At its heart, every bridge is a battle between two forces: compression and tension. Compression pushes materials together. Tension pulls them apart. A good design keeps both forces under control, using each material where it performs best. Stone and concrete are excellent in compression, but weak in tension. That's why ancient bridges relied on arches. The curve naturally channels weight down and out, keeping the material in compression. Steel, on the other hand, is strong in both tension and compression, which allows for long, slender spans. Different bridge types use these forces in different ways. Beam bridges, the simplest, resist bending by keeping the top in compression and the bottom in tension. Truss bridges spread loads through a web of triangles, making them light but strong. Arches handle compression gracefully, while suspension and cable-stayed bridges use high-strength steel cables to hold up decks over record-breaking distances. Modern materials push these ideas further. Reinforced concrete adds steel bars inside concrete to handle tension. Pre-stressed concrete squeezes the structure before it carries any load, so it resists cracking. High-performance steel and corrosion-resistant alloys keep bridges durable even in harsh weather. All of these choices come together to turn a simple roadway into a finely tuned structure, with every piece placed to balance invisible forces that could otherwise tear it apart. Bridges aren't just strong, they're built to stay safe even when something goes wrong. Engineers assume that materials will age, bolts can loosen, and unexpected forces will strike, so they add layers of protection. One key idea is redundancy. A well-designed bridge has multiple load paths, so if one beam or cable fails, others can share the weight. Truss bridges use dozens of triangles for this reason. Suspension bridges have many parallel cables inside what looks like a single main cable. Safety factors are another tool. Engineers design bridges to hold far more than their expected maximum load, often 2 or 3 times more. This margin accounts for heavy trucks, wind gusts, and even rare events like a ship striking a pier. Movement is also planned for. Expansion joints let the deck stretch and shrink as temperatures change. Bearings allow parts of the bridge to shift slightly under load or during an earthquake without cracking. In seismic regions, designers use base isolators and flexible towers to absorb shaking instead of fighting it. Wind is a special challenge. After the Tacoma Narrows collapse, aerodynamics became central to suspension bridge design. Modern decks are shaped to let air flow smoothly and avoid destructive vibrations. Cables are tested in wind tunnels before construction begins. Maintenance closes the loop. Regular inspections, sensors, and drones help spot corrosion or cracks early. America inspects most large bridges at least every 2 years. Countries like Japan add constant monitoring on major spans to catch problems before they become disasters. All of these choices mean that even under stress, storms, quakes, heavy traffic, modern bridges have built-in defenses to keep them standing and safe. Some of the world's most famous bridges show just how far engineers go to keep these structures safe. The Brooklyn Bridge, opened in 1883, was revolutionary. Its towers used a mix of granite, limestone, and steel cables, the first major use of steel wire in a suspension bridge. Designer John Roebling built it with enormous safety margins. Each cable could hold far more weight than expected traffic. More than 140 years later, the bridge still carries vehicles and pedestrians daily. The Golden Gate Bridge in San Francisco, completed in 1937, combined elegance with cutting-edge safety for its time. Its main cables each contain 27,572 wires and were built to withstand far more than the bridge's original load. Over the decades, engineers have upgraded it with seismic retrofits, wind-resistant deck designs, and even movable barriers to protect drivers. The Millau Viaduct in France, opened in 2004, shows modern precision. Its slender towers rise higher than the Eiffel Tower. But computer modeling and wind tunnel testing kept the deck stable in fierce winds. Sensors monitor strain, temperature, and vibration in real time, feeding data to engineers to ensure the structure stays safe. Even the failures have shaped progress. The collapse of Minneapolis's I-35W bridge in 2007, caused by a design flaw in a gusset plate combined with heavy construction loads, led to stricter inspections and better load tracking across the U.S. These bridges prove that strength isn't about brute force alone. It's about planning, testing, monitoring, and learning from every success and every failure. For all their complexity, bridges fail far less often than most people expect. In the United States, there are over 600,000 bridges. Each year, fewer than 0.1% experience any serious structural issue, and outright collapses are extremely rare. Most bridges are inspected every 2 years under federal guidelines, with additional checks if problems are found. These inspections are rigorous. Teams look for cracks, corrosion, and signs of fatigue. Increasingly, engineers use drones, ultrasonic testing, and fiber optic sensors to watch how a bridge behaves under real traffic. Some modern spans stream data 24/7, alerting maintenance crews to unusual strain or movement before it becomes dangerous. When failures do happen, they usually come from a combination of factors: design flaws missed decades ago, heavier loads than expected, and deferred maintenance. The I-35W collapse was traced to undersized steel gusset plates and extra construction weight. The 2018 pedestrian bridge failure in Florida showed how overlooked cracks can lead to sudden collapse. Globally, data shows the same pattern. Well-maintained modern bridges almost never fail without warning. Countries with strong inspection and maintenance programs, like Japan and much of Europe, keep catastrophic collapses extremely rare, despite older infrastructure and heavy traffic. The statistics reveal a quiet success story. While a single collapse can make headlines worldwide, the vast majority of bridges carry massive loads day after day with no incident, thanks to a safety culture built on redundancy, monitoring, and constant improvement. Bridges around the world face similar challenges, but how countries maintain and upgrade them makes a big difference. Japan is a standout example. After major earthquakes like the 1995 Kobe disaster, engineers retrofitted thousands of bridges with seismic isolators, flexible bearings, and stronger columns. Continuous monitoring is common on large spans, and inspections are frequent. As a result, Japanese bridges have survived powerful quakes, including the 2011 Tohoku earthquake, with far fewer catastrophic failures than expected. Europe takes a proactive approach too. Many countries combine strict inspection schedules with steady investment in maintenance. In France and Germany, weight limits and retrofits are applied early to aging structures. When weaknesses appear, bridges are repaired or replaced before they reach crisis. The Millau Viaduct and Denmark's Great Belt Bridge are examples of pushing technology while keeping safety first. America's record is more mixed. The interstate highway system created thousands of mid-century bridges, many now past their intended 50-year design life. Federal rules require biennial inspections, but funding for repairs often lags. About 7% of U.S. bridges are classified as structurally deficient, not unsafe to use immediately, but in need of significant work. The Minneapolis Y-35W collapse highlighted what can happen when aging designs meet heavy modern loads and deferred maintenance. The contrast shows that safety isn't just about how a bridge is built, it's about how it's cared for. Continuous upgrades, seismic retrofits, and timely repairs are why some nations rarely see failures, while others face costly emergencies. Bridges are more than just ways to cross obstacles. They're a test of how societies plan for safety over time. Each one represents decades of lessons about forces, materials, and the unexpected. Ancient stone arches taught builders the power of compression. Industrial iron and steel opened new possibilities, but also new risks. Modern failures, from Tacoma Narrows to Minneapolis, forced designers to rethink wind, load limits, and maintenance. The result is a transportation network most people never question. We cross rivers, valleys, and bays every day without fear, because generations of engineers learned from mistakes and built safety into every bolt and cable. But that safety isn't automatic. It depends on inspection, funding, and a commitment to improvement. Countries that treat maintenance and upgrades as essential keep their bridges reliable for decades. Where investment lags, aging structures become vulnerable. The lesson is that strength isn't just created when a bridge is built, it's renewed every year it's cared for. Bridges might look simple, just steel and concrete stretched across empty space, but they're the product of centuries of problem solving. Every cable, every joint, every safety factor comes from hard lessons about wind, earthquakes, corrosion, and time itself. We trust them without thinking because they're built to earn that trust. With redundancy, so one failure doesn't mean collapse, with inspections to catch problems early, and with margins strong enough to handle the unexpected. Yet their strength isn't just a feat of engineering, it's a reminder of what careful planning and long-term commitment can achieve. A bridge doesn't stay safe by accident. It stays safe because people decided it should, and because every generation added knowledge to the one before it. The next time you cross a river or a canyon without a second thought, remember, the reason you feel safe is no mystery. It's design, discipline, and decades of quiet work, all holding you up.